Here we have a second order Cauchy-Euler equation. Notice that our second derivative term is multiplied by x squared. Our first derivative term is multiplied by x. The non-derivative y term is not multiplied by a function of x at all. And this equation is non-homogeneous. So what we'll do is we'll convert this to a linear higher order ODE with constant coefficients by making the substitution. We're going to let x equal e to the t, and when x is equal to e to the t, our derivative terms, these are the terms that we just calculated in the previous slide, are going to be our first derivative, dy dx, is 1 over x times dy dt, and our second derivative, d squared y over dx squared, is 1 over x squared times d squared y over dt squared minus dy dt. So when I make my substitutions, this x squared will become e to the t squared. Actually, it won't. I'm sorry. I'm just going to keep it there. X squared, because it will cancel out with my second derivative of y, which is 1 over x squared d squared y dt squared minus dy dt minus 2x times my first derivative term, 1 over x dy dt, and again notice those x's will cancel out, plus 2y is equal to x to the third. Now here on the right side, this is where I want to make my substitution and let x equal e to the t. So I get e to the t raised to the third power. When I simplify, these x squareds will drop out. And I'm going to write this as y double prime, because once I cancel those x's, notice that all my y's, my variables are y's and my t's. So I have y is defined in terms of t. So I get y double prime minus y prime, that's this minus dy dt, minus 2y prime plus 2y is equal to e to the 3t. You can combine the negative y and the negative 2y so that we get y double prime minus 3y prime plus 2y is equal to e to the 3t. Now, here we want to start by solving the homogeneous ODE. We want to find the complementary solution by letting y equal e to the mt, and our characteristic equation becomes m squared minus 3m plus 2 is equal to 0, and that factors into m minus 2 times m minus 1, and so we get m is equal to 2 and m is equal to 1. And we get solutions of e to the 2t and e to the t. So our complementary solution is c1 e to the 2t plus c2 e to the t. Now we want to find our particular solution. We want to let our particular solution be in the form of a e to the 3t. Double check to make sure I don't have an e to the 3t term in my complementary solution. And when I substitute in, I'm going to need my first derivative. Yp prime is going to carry down a 3a e to the 3t. And my second derivative, carry down another 3, we get 9a e to the 3t. So when I substitute into this second derivative equation, I should be able to solve for a. I get my second derivative term, that's 9a e to the 3t, minus 3 times my first derivative term, plus 2 times, that shouldn't be a derivative there, plus 2 times y, well, when I combine these terms, notice this is 9a and this is negative 9a. Those terms cancel each other out. And so the only term I'm left with is this 2a e to the 3t. Which means that 2a has to be equal to the coefficient of my right side term. 2a has to equal 1. And a is 1/2. So my particular solution is 1/2 e to the 3t. And my solution in terms of t, I'll do that up here, is y of t is equal to my complementary solution, c1 e to the 2t plus c2 e to the t plus my particular solution plus 1/2. I want to go back and get my answer in terms of x. And to get my answer in terms of x, we need to make this substitution back again. Wherever you have e to the t, replace it with x. So here, e to the 2t, you could write as e to the t squared. And that'll make this substitution back really easily. So I have c1 e to the t is x. That'll give me x squared plus c2 e to the t, that's an x, plus 1/2. And there's my solution in terms of x. So the nice thing about making this substitution is that it changes it into the type of equation that we have been working on. And the only thing you need to remember is that at the end, make sure that you switch your answer back so that your equation is back in terms of the original variable, which is usually, at least in this course, it's an x.